I'm from Australia, from the CSIRO, which is our government research organisation, and I work in a lab there, the Health Research Centre. I've been heavily involved in SNOMED, as you can see, for some number of years, down in the technical weeds mostly. I was the primary author of the SNOMED URI specification, which has a lot of use in the FHIR terminology services spec. Heavily involved in the expression constraint language, which I will also introduce here, and co-developed a number of tools which will come up during this. And also our terminology server is part of Australia's National Clinical Terminology Service. It uses the FHIR terminology service APIs quite heavily, and hence the t-shirt. And if you have any questions you want to ask me about that after the session, then come on. So some of the tools, Shrimp, you may have seen. This is a terminology browser using only FHIR APIs. Snapper's probably come up in a couple of presentations. It's primarily a terminology resource authoring tool. It's a work in progress. We've just updated it to SQ3 support. It's fairly useful. It doesn't do everything, but it does the simple things fairly handily. If you're playing with different terminology servers, you can use this Explorer tool to try out the behavior of expand with filter against different server endpoints to see how they perform. And so that's enough about me and my things. So can I get a show of hands who attended the introductory terminology talk this morning? Okay, so about half-ish, I think. Who's used terminology services in FHIR? Okay. Has anyone implemented any of the terminology services in FHIR? Much smaller group. SNOMED knowledge. Oh, excellent. More than I expected. So you're going to have a little snooze at the beginning bit. Other code system knowledge. So, is that nice? Okay, and would that be like Lawley, RX norm, those sorts of things? Okay, excellent. So just as a setting the scene, this is the terminology services big picture. So we have code systems subsetted by value sets, and then concept maps are used to translate between usually different code systems, but perhaps within a code system. And if you're in the earlier session, there's a question about naming scheme, and they're not prominent here. So to sort of answer that question, they represent a way to talk about a code system that's non-authoritative. So they're really just saying, this system exists, and here's some stuff I know about it, but it's not an authoritative statement about it. It's not really useful for any of the terminology operations, so it pretty much slips off the radar. We ran a little short in the previous session, so this is the key slide that was missed out. And it's about terminology in the FHIR search operations. So key things here are the above and below qualifiers on a code-based search, and the in and not in, so this allows you to basically do subsumption style searching, and the in not in allows you to do searching based on value set membership. So FHIR spec talks about a number of externally defined code systems, and this is where things get a lot more interesting. So, simple FHIR code systems, you can define properties and filters, and they interact with the various operations. But these things tend to come with a whole lot more complexity and baggage, and I say that lovingly. SNOMED comes with a lot of its own. And so we'll just do a quick overview because you need to understand some of the operations, some of the internal structure of how SNOMED works to get a feel for some of this stuff. So overall, SNOMED is a hierarchical code system where it's a subsumption relationship. The hierarchy is a subsumption relationship. There's approximately 400,000 concepts. Not all of them are active. A large portion of them are. And that number varies depending on whether you're talking about the international version of SNOMED or some of the national releases. So, for example, the Australian version of SNOMED has about 100,000 extra codes which cover medications, so generics and branded medications. Every code has a preferred term, so the thing that you should normally display. It has a fully specified name, which is its actual meaning. So it's actually the source of truth for the meaning of a code. And then some synonyms. And I use the term synonym loosely because some of them are synonymous and some of them aren't. And so you need to be careful of that in your use of SNOMED. There are about 65 attributes, and they're used to define cross-concept relationships. So for example, if you have a clinical finding like appendicitis, appendicitis is defined with relationships to the appendix structure and to the morphology of inflammation, and that internal structure is used to carry knowledge about the meaning of the codes, and it's also used to maintain the integrity of the code system. So that's how you get quality in a code system of that sort of size. It's not perfect, but it's pretty good. So now a quick little demo. So this is the Shrimp terminology browser. What you can see here is the top level hierarchy of the Australian version of SNOMED. That's why it's got two root concepts there. So the Australian extension sort of sits off to the side. I'm going to have to drive this looking sideways. And looks like we have some significant network latency issues. Okay, so as I'm typing there, we're getting expand requests being sent off to the terminology service, and the expansion results coming back, and then we display those expansion results with the labels there. And mouse. Select the code. What we're doing now is sending off a number of other requests. And normally you don't see this, normally it's lightning fast, but with the latency we have at the moment, you're actually getting some delay here. So it's trying to get the hierarchy for that code. So sending off a request to find all the ancestors and all the immediate children of that code to then render a hierarchy, and also a lookup to populate the set of properties here. And also a request to for a binary resource, which happens to be this SVG object that shows the definition of the code. So this is what I was talking about with the relationships. So this is the SNOMED diagramming rendering of what the relationships are. So acute appendicitis has a parent of appendicitis, and these relationships to acute inflammation and the appendix structure. And that's important for some of the later stuff on expression constraint, the expression constraint language. Okay. It's going to be very tedious. This going.
in your URI.
Ah, great. Excellent. Okay, so got rid of the latency, and now you can see the sort of behaviour that's going on. So all of this is done just by straightforward FHIR requests, and just look up something. This is looking up the medicines terminology, and down here, all these properties have come back from the lookup request, except this last one here, which is the TG ID. That was actually has come back from a translate request. So we've done a translate on the code using a concept map to find the corresponding. That's a regulatory authority code. So those are some of the sorts of things that you can do. You see this is interactive use, it's performant, and it's just using those straightforward APIs. Back to the slides. Okay, so there's a number of gotchas that come up here, and these are some of the things you need to be aware of. When you're doing that sort of incremental search or type ahead type search, you need to be beware of out of order responses. So as you start typing, your system will be sending off expand with filter requests. They'll all be independent, and then the responses will come back, and they may come back out of order. And that often happens because when you start typing, it's very short string. You get lots of matches. It's actually slower because there's more data coming back. When you type longer things, it's much quicker. So you need to make sure that you take care of that. And standard libraries for these sorts of autocomplete widgets generally handle that for you, but not all of them do. So if you start seeing some strange results where the search results don't match up with what you've actually typed, then that's probably what's happened. You've got a stale response coming back that you're rendering. You want to minimize latency, so there's a couple of ways to do that. One is to batch up operations, so you can do a batch request. So that's just posting a set of FHIR requests in a single interaction. That gives you a single round trip, which is a good thing. It avoids the need for that client-side synchronization. If you're sending off multiple requests and you need to wait for them all to have completed, you don't need to do that yourself because you just get that one batch response. The downside is that the batch request is a post. You cannot cache posts, at least at the HTTP level, so you don't get free caching. So you may actually end up costing yourself. So again, it's one of those things, if you're optimizing, you've got to measure. Minimizing bandwidth, when you do your expand, you want to specify a count to say this is the maximum number of things I want back, because you might get back a lot of responses. Also, some terminology servers, many terminology servers, have a cap on the maximum number of things they'll return in an expand. So you want to avoid hitting that cap and getting a too costly result. There are a number of, as we saw earlier, a number of other parameters that you can pass, like include definition, include designations, and so forth. You can use those to tailor what results come back. In a lookup request, you've got the property parameter, which allows you to tailor the set of properties you want to come back. Because some will come back as defaults, but there may be others you need to explicitly request. And things that you don't want to come back. So again, minimizing the size of the response. For search and read operations, the sort of generic scrub type operations, you've got paging with underscore count, and you can tailor what elements come back in the result with the underscore elements parameter. Not all servers actually respect these, but they should. And then accept encoding GZ header, so you can have the responses compressed, and that again can have a fairly significant effect on caching and performance in an interactive environment for that sort of type ahead result. And as I said before, gets can be cached at the HTTP level, posts can't. And a lot of this behavior is server dependent, so you need to test and choose something that has the behavior you need. So Jim introduced implicit value sets. Implicit value sets for these well-defined code systems like SNOMED and LOIC are basically URI patterns that imply the existence of a value set, or you talk about a value set that may not have an explicit existence in the server, but has a well-known definition. And so here are 4 that are defined for SNOMED. The first one says I want all the codes in SNOMED. That includes the inactive codes, so it's just all codes in SNOMED. Second one is all codes equal to or below the code that you supply at the end there. This is all reference sets defined in SNOMED, so it gives you back the codes for the reference sets. And reference sets are the SNOMED notion of a subset of codes, so they're equivalent to the expansion of a value set. Generally, there's other stuff. There's reference sets for maps and for other purposes, but generally when we're talking here, we're talking about lists of codes for a particular purpose. And then the last one says, give me the codes that are actually in this reference set. So how might you use these? Well, if you want to follow along, there's a plunker there. The slides are available, so you don't have to copy it down if you don't want to. So with a simple type of head control like the bootstrap, angular bootstrap type of head control, this is kind of the minimal thing that will give you a type of head control. And really what we're saying here is call this function concepts and give it the text that the user's typed so far, so that's the view value. And this is the value set that I'm interested in. And that one happens to be, that concept is the SNOMED root concept. So that gives you everything that is a SNOMED concept, which is in fact all the active concepts. And then this is our concepts function, which is just doing a get to our terminology server, doing an expand, supplying the value set parameter as the value set that we want to expand, and the filter parameter is the text that the user has typed, and we're asking for first 15, and we want JSON coming back. And we're actually specifying this. This is how you would specify it in the headers, and this is the FHIR way of doing it. And then no error handling here. So we're assuming that when we get back an expansion, we want to return up to the type head layer the actual set of codes that came back in that expansion. If we don't get a response here, we're just going to return the text itself, so it gives you at least a fallback. And if you go to this plunker, you'll find an implementation of that with additional stuff, and you can modify it and play with it. If you want to do something like the value set that's all diabetes codes, all you need to do is use the diabetes code there in the implicit value set URL, and you've got a type ahead for that. And if you want to vary the number of results that come back in your type ahead, you can change the count parameter. So it's very easy to get a simple control up and running in the user interface. No value sets created here, it's all just implicit stuff. So, now this is a bit of a grab bag. I want to sort of dive off into SNOMED versioning here, because versioning in the SNOMED space with an international audience is a bit of a complex beast. So the international release currently comes out every 6 months. Different national releases come out on different schedules and different rates. So we see between every month and every 6 months, but offset from the international release. And then you may have other releases. So you may have a local jurisdiction or a hospital, or your own organisation may do its own extension of SNOMED and have your own releases there. So there's a whole lot of different versions going on here, potentially. And we need to be able to talk about what version is in play to have complete information about a code. And the basis of this is that a version is a combination of the edition. So is it the international edition? Is it a national edition? Is it your local edition? Plus the effective time. So effective time is the release date of your version. And that is then rendered into a version string which has this format, and that gives you a machine readable mechanism to describe the version, and with the SNOMED release format you can pull that apart and identify what content is relevant. That's different to many other versioning systems that you get for most other code systems, and in fact most things. Within an edition, you effectively have a linear set of versions. So at a point in time, you've got a version, and then you've got another version, and then another version, and that's simple. But with another release, you've got other versions coming out, and they're sitting parallel. And so there's a diagram of the Australian releases, and then hypothetical series of US releases. And you'll notice that at any given point in time, there isn't a single latest version. And that's kind of important for terminology services, because when you don't specify a version for all the operations, the interpretation is to use the latest version. Here, there isn't a latest version. So in fact, we'll see at this point in time, this is the latest AU version, but this is the latest international version, and this is the latest US version. And oops, this version depends on that international version, but this one depends on that international version. So you can't just take the union of them, because then you end up with effectively version skew and conflict. So this is why it gets complex, and why your terminology server, if it's dealing with cross-jurisdictional issues like this and multiple versions of SNOMED, needs to understand this and be smart about it. If you look at our terminology server, we have the notion of a default edition. So when it's resolving the latest version, it's doing that against the default edition. But otherwise you have to specify the version explicitly. Now that impacts implicit value sets. So I showed you before, these are the template URLs for implicit value sets. What you can do is, instead of just having this part of the implicit URL, you can specify additionally the module ID. So if you want to say this reference set in the Australian edition, not a specific version, but just the Australian edition, then you can use this as the prefix, so replacing the blue bit with all of this and the Australian module ID. If you want to talk about a specific version of that, then you can add in the effective time there, again replacing the blue part with all of this string. So implicit URLs for SNOMED come in version neutral forms, edition specific forms, and then version specific forms. So you've got a lot of ability to play around with that. And so this is when you're defining a value set. We're talking about the system here. System would be SNOMED, and the version will be one of those version strings or empty. So you can do that, and you can also provide just the edition version string there, and that should then result. Says that this value set is defined with respect to that edition of SNOMED. It's a little bugbear at the moment with the value set resource is that there's this notion of the locked date field where you can say you put a date in and it gives you a fixed date for interpreting the definition of the value set. But as we saw, there is no single version that you can resolve that to for SNOMED. So locked date is a bit of a problem there. It perhaps should be locked version if it's useful. We haven't actually seen anyone using locked date, but that may just be something that's specific to Australia and different in other jurisdictions. Okay, so defining the contents of a value set, we specify a number of different ways to include things in. So you can specify a set of concepts, but when you're specifying a set of concepts, you've got this additional stuff that you can specify. So you can optionally specify display text and some additional designations. The intent here is that you can do some tuning of the display text for in the context of the value set. So it lets you do things like interface terminology things. So for a particular value set that's intended for a particular use case, you may not want to take the default display text. It may be cumbersome, or it may not be quite what you want to appear in the display. So you can specify something different here. Similarly, with you may need to support other languages, so you could specify other designations there, and so that would provide those things specific to that value set. Having said that, there's not very many terminology servers we've seen out there that actually do anything with this. Some of them just pass it through. So when you do the expansion, and you get back the codes, you'll get this carried forward. But this data might not be used for doing the filtering. So if you've supplied a different display text, it may not actually take part in the search matching. Others ignore it completely. So again, your mileage may vary. This is the really interesting part of value set compose is the filters, and I'm going to be specifically talking about the constraint property filter for SNOMED and how that's used with the expression constraint language. And then finally, we've got the value set include. If you specify multiple value sets, you're saying include the intersection of the contents of these value sets. If you want the union, you have to do multiple includes. So you've got different levels of multiplicity going on here. So it's inside an include, you're doing the conjunction of the constraints. Outside, you're doing the union of the includes. And then the exclude is the same internal pattern. The evaluation mechanism here is important. All the includes are resolved first, and then all the excludes are done afterwards. So there's no sort of interacting, strange interactions between ordering that can go on between includes and excludes. There are some interesting things that you can do though. With you can actually set up cycles with your includes and excludes, and different terminology servers again behave differently when you do that. Some of them will go into an infinite loop. Others will apply some kind of fixed point semantics, which is potentially helpful. And others may detect it and then just say, sorry, you've got a cycle, can't do it. It's worth playing around and experimenting. You can mix code from multiple code systems into one value set. Please don't. I know there are some practical scenarios where you just have to do that. And perhaps when you're doing profiling, it may be the kind of thing that you need to do to say, you could have things from here and from here. But for interoperability and data that you can actually share and interpret and exchange with any sort of useful meaning, mixing code systems just creates havoc. Last thing you can do that's kind of interesting is you can actually have a value set that's defined in terms of different versions of the same code system. Again, mileage may vary on the terminology server itself, but as a practical example of why you might want to do this, here's a definition that includes all the descendants of SNOMED root concept from the October version of SNOMED and excludes all the codes, same set of codes, but from the November version. So it's going to tell you, when you do an expand, what are the new codes that came in the October version that weren't there in the previous version. And that may be really useful if you want to know, well, what's new? I need to update some concept maps to account for these new codes. So some back office kind of things, these sorts of multi-version value set definitions can be quite handy. Okay, so expression constraint language. This is only recently been defined by SNOMED International. It's effectively a simple query language for SNOMED concepts. It's based around the post-coordination syntax, which I'll talk a little bit about further on. And it basically gives you a number of ways of defining constraints across SNOMED code. It gives you a wildcard operator, descendants and ancestor operators, reference set membership, and cardinality constraints. Now, most of those things you can do just with normal filters in a value set, so with the parent or child properties on a code. But the cardinality constraints are really powerful within that, and this is SNOMED native, so you can go a long way there. And it will eventually evolve into a much more complete query language where you can interact with other properties of the SNOMED codes. To use this in a value set definition, you use the constraint property equals, and the value is your expression constraint language expression. So here's a very brief summary of what the language looks like. A single code by itself is an expression constraint and matches the code. Star matches any code, including inactive codes. The caret is membership, so members of a reference set identified by the concept ID. These give you descendants and self, descendants and immediate children, and then the equivalent ones for ancestors, so going up the hierarchy. You can compose sub-expressions together with and, or, and difference. And you can do relationship-based constraints. So you can see an example there. This is saying, find me all descendants of this concept, which is clinical finding, that have a finding site that is a lateralizable body structure. So that would actually identify all the clinical findings that you could apply left or right laterality to. So it's a handy sort of constraint. And then cardinality constraints, this is saying, find me the things that have exactly one finding site. So, really hard to drive. Hey, within Shrimp, we actually have exposed the ability to play around with the expression constraint language, so you can do live exploration of this, and there's also a useful help page, which is a more expanded version of the table I just showed you. Shows you all the syntax, including the long form, so I just showed you the symbolic form of descendants and so forth, but there's also textual forms, which is a bit more human readable, but worse to type. And then a set of live examples of each of the different forms that when you click on will take you through to the expression constraint evaluator, and then we're going to have network issues. So if we had the expression in here, then we would have been able to evaluate that. So I'll just give you a quick demo here. So okay, so it has no descendants. It's an unlucky choice. It will have ancestors. So there are the ancestors. So again, what's happening here is that we're constructing a FHIR value set on the fly with the compose with the filter and posting that to the terminology server and getting back the expansion. Okay. Said I'd talk about post-coordination. So SNOMED has the notion of post-coordination, which allows you to put together multiple codes to capture meanings that aren't already don't already have a single code in SNOMED. So, for example, fracture of the left femur here. So we've taken fracture of the femur, we've said laterality left. So this is what's called a post-coordinated expression. FHIR has usefully said that any post-coordinated expression is also a valid SNOMED code. So anywhere that you can have a SNOMED code in FHIR, you could also have a post-coordinated expression. That's really great. So you can do some useful sorts of things. So here I'm saying I've got appendicitis with actually acute inflammation as my morphology, or I've got a disease with morphology of acute inflammation and a finding site of the appendix structure. These are two different post-coordinated expressions that are actually equivalent to acute appendicitis. As a consumer of these sorts of expressions, it's a lot of heavy lifting to work out that those things were equivalent. That's the sort of thing that you want your terminology server to do. Hence, we have the subsumes operation, which is intended to understand how to put these things together or pull them apart to determine equivalence or subsumption relationships. So the subsumes operation, you give it code A and code B. Those codes, either or both, could be expressions. And you say, is there a subsumption relationship between these two things? And you'll get back one of 4 answers. Either they're equivalent, one's a parent of the other, or vice versa, or they have no subsumption relationship. The terminology server can do all that heavy lifting so that you don't have to. That's great if you've got 2 things that you want to compare, but when you've got lots of codes, then you're going to need to use the closure operation. And I'm going to have to really race to get to that. Compose is another operation. It's pretty immature, so ignore compose. So quickly whip through the closure operation because this is really useful and important. It's how to use it is actually documented not on the operation page itself, but in this other part of the spec. It creates state on the server. It's a kind of transient state. And a lot of people ask, why? What's this closure thing for? How do I use it? So imagine you have a health record system, supposing a FHIR API, and you're supporting code below searches. So doing a search on all codes that are descendants of tumour of liver, and you've got all your clinical data sitting in your EHR, but you've got your terminology sitting in another server, in your terminology service. And really, to do that, you need to do some join, right? You need to find the set of codes, or the set of things in here that have codes that are descendants of that thing. So how do you do that? You don't want to have to replicate all of that subsumption stuff in your system. So basically, the closure table allows you to take these subset of codes that actually occur in your clinical records, incrementally build up the transitive closure of the subsumption relationships between just those codes. And effectively what you're doing is sucking out the codes from the terminology server, those relationships from the terminology server, and caching them locally with your data. So in a stepwise manner, and as you get new records added, new codes occur, you can say, well, I've got this new code, tell me any new relationships I need to know about. If you lose any state here, there's a resynchronization capability. But you maintain that edge table, it's a transitive closure of edges, and then your code below search becomes just something like this. So you have your edges table, and that contains all the things that you're looking for, and you've got a very simple join query to do that code below search. But you haven't had to deal with post-coordination, you haven't had to deal with different code systems do their hierarchy and subsumption stuff differently, you haven't had to deal with any of that. All that's been handled by the terminology service. So I think I'm pretty much out of time. I've got a couple more slides, but they're available. So maybe a quick question, if anyone has a question.